And we plan to sort of make it available through YouTube. So I think that should be okay with you, right?
Yeah, that'd be great.
Awesome, thank you. So I think let's get started. Welcome everyone. If you are not from West Lafayette, we had a little bit of the snow last night. So hey, great spring, extended spring with close to 0 degrees Celsius temperature. Can't complain. So with that sort of a warm welcome from West Lafayette, it's my great pleasure to welcome a very good friend and colleague from Columbia University, Professor Lauren Marbella. And I have met her, listened to her talk, read her papers. It's just wonderful to see, to see some of her work here today. With that, the formal introduction will be done by the chapter president, Deepanjali, and a big thank you to Lauren for finding time today. This is a very busy time of the year. I was just speaking about that. And with that, let me hand it over to Deepanjali for the formal introduction. Thank you, Lauren.
Thank you, Professor Mukherjee. Let me share my screen. Is my screen visible?
Yep.
Okay. So hello, everyone. Welcome back to our webinar series. I am Deepanjali Chatterjee, a second-year PhD student at the Energy and Transport Sciences Lab and president of the ECS Purdue Student Chapter. I would first like to introduce our chapter advisory board. We are led by Professor Partha Mukherjee from the School of Mechanical Engineering at Purdue, who is our lead faculty advisor. Dr. Judy Jivarajan, Corporate Fellow and Vice President of Research at Underwriters Labs, is our distinguished industry advisor. We also have Professor Rebecca Chase from the School of Mechanical Engineering and Professor Julia Laskin from the Department of Chemistry at Purdue as our co-faculty advisors. Let me present a quick overview of our chapter activities over the past year. In spring 2021, we conducted our signature webinar series on women in electrochemical sciences and engineering. Comprising of a stellar lineup of women researchers from industry, national labs, and academia, this series was extremely well received and appreciated in the scientific community. Inspired by its success, in fall 2021, we launched a webinar series on one of the hot topics in energy storage research, solid-state batteries and electrochemistry, inviting some of the leading academic and industry experts in this area. We are proud to announce that for our efforts in actively promoting scientific engagement and outreach on a global scale, we were awarded the 2021 Chapter of Excellence by the Electrochemical Society. The theme of this year's webinar series is Modeling, Characterization, and Analytics in Electrochemical Energy Systems, abbreviated as MoChA. Today's speaker is Professor Lauren Marbella from the Department of Chemical Engineering at Columbia University. Professor Marbella received her PhD in chemistry from the University of Pittsburgh in 2016 under the direction of Prof. Jill Millstone. In 2017, she was named a Marie Curie postdoctoral fellow at the University of Cambridge in the group of Professor Claire Gray. There, she was also named the Charles and Catherine Darwin Research Fellow, which recognizes the top junior fellow at Darwin College at the University of Cambridge. She joined the chemical engineering faculty at Columbia University in 2018. Professor Marbella's research group focuses on understanding the relationship between electrochemical performance and interfacial chemistry in devices for energy storage and conversion. Her research relies heavily on the use of nuclear magnetic resonance imaging, MRI, and spectroscopy to evaluate changes in material properties in real time to elucidate the chemical mechanisms underpinning degradation in lithium and beyond lithium-ion battery systems. Professor Marbella is the recipient of numerous awards, including the Cottrell Scholar Award, the National Science Foundation Faculty Early Career Development Award, and the Scialog Collaborative Innovation Award for Advanced Energy Storage. Today, she will be speaking on resolving chemical and spatial heterogeneities at complex electrochemical interfaces in lithium-ion batteries. Professor Marbella, we look forward to your talk.
Thank you so much for a very kind introduction. I'm going to go ahead and share my screen. Okay. There we go. 1 second, I'm going to make everyone's head small and get my pointer. Okay, so thank you again for this wonderful invitation. It's really exciting to be here and talk to everyone about some of the work that my group has been doing at Columbia over the past few years. Oops. So I'd like to start off by just telling you a little bit about what motivates our interest in this work, and what really sort of drives us in the lab every day is this interest and this motivation to be able to study systems that can help address the major challenges that are facing the world today because of climate change. And whenever you hear someone talk about climate change, you often hear this sentence that's listed at the bottom of the slide, where if we want to stop some of the most devastating impacts of climate change, we have to reach this net zero carbon emissions by 2050, so that we can limit this temperature increase to about 1.5 degrees centigrade above pre-industrial levels. So one proposed way that we can do this while we can still have all of the commodities that we're used to in modern life is an integrated system that I'm showing you here. This was proposed a few years ago in Science magazine. I'm not going to go into the individual details of this integrated system, but because this is for the Electrochemical Society, I just wanted to point out the very critical role that electrochemistry is going to play in actually developing one of these integrated systems. So we already see that lithium-ion batteries are playing a very key role in things like electrified transportation. We know that we're going to need to introduce things like fuel cells and electrolyzers to continue to tackle some of these challenges. Batteries are also going to play a key role in stationary storage, so things like wind and solar, these very intermittent sources of energy. And then, of course, if we want to continue to feed our ever-growing global population, we're of course going to want to come up with cleaner ways to produce things like fertilizers. So how can we use things like electrochemistry to produce things like ammonia in a much cleaner way than they're actually being produced today? And basically the main point here is that electrochemistry is going to be a very important component of many of these solutions. So if electrochemistry is going to play a key role, we want to be able to make electrodes. Electrodes, of course, are a very important component of electrochemical systems. So if you're familiar with making batteries, or even if you're interested in fuel cells or heterogeneous catalysis, the way that we go about fabricating electrodes is similar in a lot of these systems. So my talk and the interests in my group are focused on lithium-based batteries, and the way that we go about making these electrodes is by combining our active material. Today, I'm going to focus on the cathode side of the battery. So our active material is usually some type of transition metal oxide. We're going to combine this powder with some type of conductive carbon. This is so that we can increase the electronic conductivity of the material. We're going to combine this with some type of solvated polymer. Usually this is something like PVDF. This will produce an electrode ink. This electrode ink can then be cast onto our current collector. It can be dried, and then we have our final electrode, which can then be placed in our electrolyte solution whenever we make and fabricate our final battery that's actually going to do the work and supply the power to our system. That's all great and well, but at the end of the day, because we're actually making these composites, what we're left with at the end that's actually interfacing between our solid electrode and our liquid electrolyte is a very complex, multi-component, porous electrode that's actually interacting with that liquid electrolyte solution. So here's an example TEM that's a very dramatic example. So this electrode hasn't been calendared or anything like that, but it's really just to show you what a composite cathode looks like under an SEM image. So what you're looking at here is a nickel-rich transition metal oxide active particle shown in orange, and then our carbon additives, so our conductive carbon and our polymeric binder, are shown here in gray. Oops. So the system that we're going to be talking about today is the lithium, nickel, manganese, cobalt oxide active particles. Those are actually what's shown in the SEM image here. So this is abbreviated Nmc811. That's what you'll hear me talk about for the remainder of the talk today. This is a layered material where you have your transition metal oxide layers, your lithium intercalates in between these layers, and intercalates and deintercalates during charge and discharge of the battery. The liquid electrolyte that we're going to be using in this system, the salt that we're concerned with today is lithium PF6. And the solvent that we have in this system is a 1-to-1 mixture of ethylene carbonate and dimethyl carbonate. So both a cyclic and a linear carbonate molecule that's actually making up our solution here. So the reason that we're interested in NMC811 is we're trying to move away from these cobalt-based batteries. So replacing a lot of the cobalt in the system with nickel and manganese, eventually moving towards also a more manganese-rich composition in the active particles here as well, so that we can alleviate some of the geopolitical concerns over continued cobalt mining. Unfortunately, the issue is whenever we start to remove cobalt from the active particles in these systems, is that the NMC811 starts to suffer from capacity loss and impedance increase whenever we start cycling the battery. And this is due to a variety of interfacial degradation modes that occur in these systems. So the first one that I'm showing here on the left is due to electrolyte solvent degradation that occurs at the interface between these active particles and the electrolyte solution. We also have a transition from the layered architecture within the active particles to this rock salt-like structure on the surface of the NMC811 that leads to this increased resistance during extended electrochemical cycling. And then you'll actually notice in this SEM image that these are not primary particles, they're actually secondary particles of NMC stuck together. So whenever you have these mechanical strains during lithiation and delithiation of this material, the secondary particles undergo cracking. This exposes fresh surface where you can have either electrolyte decomposition or rock salt formation on the surface of the freshly exposed particle surface. So we have two mechanisms here on the right, the rock salt layer formation and the particle cracking that can be readily studied by techniques like electron microscopy. So this is a high resolution TEM image shown here. This is a tomography image shown on the right. But things like the electrolyte decomposition are a bit harder to study because we have the formation of these very fluffy organic decomposition products that are depositing all over the surface of this very heterogeneous composite. So these aren't going to diffract very well in things like an electron microscope. So they're much more difficult to understand the structure and the composition of. From a fundamental perspective, actually understanding the origin of this cathode electrolyte interface is also quite intriguing. At the voltages that we are operating our lithium-ion batteries, we might not necessarily expect an interface to develop. So the interface on the cathode side of the battery is abbreviated the CEI, whereas on the anode side of the battery, we're calling it the solid electrolyte interface, which is abbreviated the SEI over here. So you can see from this diagram here, this blue bar represents the electrochemical stability window of our carbonate solvent molecules that we're using in the electrolyte solution. So you can see that whenever we're cycling this battery to 4.2 volts, we wouldn't necessarily expect carbonate breakdown just based on thermodynamics. So if we're thinking about where this interface is coming from, one possible route might be from chemical crosstalk. So these carbonate molecules are well known to be reduced on the anode side of the battery. If there's any soluble species that are formed, they could migrate across the separator and be deposited on the cathode side of the battery, building up an interface on the positive side. As we move from a cobalt-rich composition like lithium cobalt oxide to something that is more nickel-rich like NMC811, we're actually changing the chemistry of those terminal oxygens and And we are also changing the reactivity of those surface oxygens. So we are increasing the nucleophilicity there. So it's also possible that those surface oxygens can attack the carbonate molecules. So it might be a chemical mechanism of decomposition that's causing the buildup of this interface layer on the surface of our active particles as well. And of course, as we're incorporating more nickel into our active particles, things like nickel 4+ on the surface of the material can also lead to decomposition of the electrolyte solvent itself. And then, of course, I also showed you this SEM of the cathode composite. And we also not only have to be worried about the reactivity of our active particles, but we also see that we have those carbon additives there. So it's also possible that things like our conductive carbon and our PVDF could interact with our electrolyte as well. So we have multiple components here that can interact with our liquid electrolyte and possibly contribute to interface formation on the cathode side of the battery. So ideally what we want to be able to do is be able to visualize this interface with high chemical and high spatial resolution to actually understand where and how electrolyte decomposition occurs during battery operation. So what I'm showing you here is a few different techniques that give us that spatial resolution that we need to actually start to distinguish where electrolyte decomposition is taking place on the composite surface. So the first one here is X-ray photoemission electron microscopy. So this is a synchrotron-based technique where we're essentially collecting spatially resolved X-ray absorption spectra. So what you're looking at here is the K edge shown in red, the F edge shown in green, and you can see that you get a spatial resolution on the order of about 70 nanometers. So we're talking tens of nanometers here. The active particles in these systems are usually on the order of 1 to 10 microns. So this is suitable to actually be able to distinguish where you have electrolyte decomposition on the composite, whether it's on the active particle or the carbon additives. Similarly, at the lab scale, you can also perform X-ray photoelectron spectroscopy imaging. You can also do TOF SIMS, so mass spectrometry based techniques or XPS based techniques to actually start to understand the chemical composition of what is deposited on your composite surface. At the lab scale, your spatial resolution here is going to be limited to about 200 nanometers. So a little bit less well resolved than the XPM approach, but still good enough to actually be able to distinguish whether you actually have decomposition on your additives or your active particles here. And then, of course, we can borrow techniques from structural biology, so things like cryogenic electron microscopy, to actually start to assign the different chemical components that are present in our CEI on the surface of our cathode. And here, if we have a component that is crystalline, because we're actually looking at the individual lattice planes from these different components, we can get atomic scale resolution. But of course, the catch is here is that the species that we're looking at has to be crystalline in order to definitively assign the chemical composition here. One thing about all of these individual techniques is that they all have to be performed under ultra high vacuum conditions. And what this means is that in order to actually collect this data is that we have to wash the sample so that there's no charging under ultra high vacuum conditions. And whenever we wash the samples, this inherently means that we might be disrupting this very delicate interface layer that's built up on the battery during electrochemical cycling. So while these techniques are providing exceptional spatial resolution in the lateral dimension, we ideally want to be able to couple these techniques with something that's able to analyze the interface chemistry in a more native operating environment to the battery. So what we're interested in my group is how can we couple these laterally resolved X-ray measurements with something that's a little bit less invasive, something like NMR spectroscopy. So we've had a lot of success in my group in being able to study both the spatial architecture of the SEI that's deposited on the surface of electrodes using multidimensional NMR spectroscopy. This is an example of the arrangement of the SEI that's deposited on the surface of a lithium metal anode. The nice thing about NMR spectroscopy is that in addition to structural information, you also have the opportunity to learn something about the dynamics of the SEI layer as well. So I'm not going to have time to talk about that today, but just something to note that you always have the opportunity to start to actually analyze dynamics because you're doing a type of spectroscopy. And then, of course, because you're doing something non-invasive like NMR, you always have the opportunity to perhaps start to analyze these systems and start to monitor electrolyte decomposition in real time. This is something that I will talk to you about today for the NMC system. So how can we actually start to monitor electrolyte oxidation reactions so that we can actually understand why these electrolyte components got deposited on the surface of our cathode in the way that they did. So before we get into that, the first thing that I'd like to talk a little bit about is, why it's actually so challenging, particularly on the cathode side of the battery, to analyze the CEI. So in all technologically relevant cathodes, you have some paramagnetic center that's in the active particle. So if we think about things like NMC or LFP or LMO, we always have some type of paramagnetic transition metal. So we're talking about things here like manganese, cobalt, nickel, iron, something in that active material has an unpaired electron. What's deposited on the surface of your electrode is very likely diamagnetic. So if we think about common components in the interface, we're mostly talking about things like lithium fluoride or lithium carbonate. These do not have unpaired electrons in them. These are readily observed by NMR, and these shouldn't present any problems. The only time that they're going to present problems is when they are actually appended to a substrate that is paramagnetic and actually has an unpaired electron in it. The reason for that is that these unpaired electrons can actually couple to nuclei of interest in our interface. This has a distance-dependent effect, and it impacts different NMR parameters in our experiment. So the NMR parameter that we're going to care about most in the experiment that I'm going to talk to you about today is something called T2. This is our spin-spin relaxation. And it has this distance-dependent effect. So R here represents our inner spin distance between our unpaired electron and our substrate. And this is just a nuclear environment that we're interested in studying in our interface. So things that are very close to our paramagnetic substrate are going to be impacted the most. Things that are very far away in the outer CEI are going to be impacted the least. The reason that we care so much about this T2 parameter is because it's inversely proportional to the full width at half max of our NMR line. So if we think about something like lithium carbonate, which would normally give a very sharp line shape in NMR, like this black line that I'm showing here. When we put it near an electron, all of a sudden, its T2 is going to become very short, and it's going to give a very broad NMR line shape, like this blue line that I'm showing here. Oftentimes in solid state NMR, in order to get high resolution spectra, we're also going to be mechanically rotating our sample. And because we're mechanically rotating our sample, we get something that's called a spinning sideband pattern. So this very broad line shape is also going to be broken up into this spinning sideband pattern that looks something like this, where we get a peak that coincides with our normal isotropic peak that we would expect for lithium carbonate. But then it's going to have this sideband manifold that is sort of enveloped by this very broad NMR line shape that's coming from coupling to this unpaired electron from the paramagnetic material that's underneath it. So sometimes this broadening effect can be so bad that our NMR signal is actually completely broadened into the baseline and you get no signal at all. So that's basically worst case scenario. So we want to stay away from stuff that's very, very paramagnetic because we're actually not going to get any signal from those types of materials. So if we think about Nmc811 and we look at the electron configuration of all of the different transition metal centers that we have in this material. So let's take just the pristine material that we have here. We have our nickel, it's in a mixed 2+, 3+ oxidation state. Both of those are paramagnetic. Nickel makes up 80% of our transition metal centers here. So this is already bad news bears. This is not a good starting place if we actually want to be able to analyze the surface chemistry of whatever is appended to Nmc811. Manganese is in the 4+ oxidation state, also paramagnetic, not helping us. The only thing we really have going for us here is the fact that our cobalt is in the 3+ oxidation state. This is diamagnetic, but cobalt really only makes up 10% of our transition metal centers here. So it's really not going to be that helpful to us. Most of our material is very strongly paramagnetic here. So the chances of us getting highly resolved NMR signal here is highly unlikely. So, I was just starting out as an assistant professor, and I was very excited about the prospect of being able to characterize the CEI with NMR because you get such great resolution with something like carbon NMR spectroscopy that you're really not able to attain with something like X-ray spectroscopy. But this was just a very demoralizing chart to look at. So whenever I took my first PhD student to work on this project, I thought we ought to start on something that was a little bit easier. So the first thing that we ended up studying was the CEI that's appended to the lithium ruthenate structures. And we were interested in these ruthenates because they have these ruthenium dimers in them that actually serve to quench one of the paramagnetic sites of ruthenium in this structure. So my idea was, if we were actually going to be able to obtain NMR of the CEI of any material, it was very likely going to be the ruthenates. The ruthenates were also just very fundamentally interesting as well because they have this nice 4+, 5+ oxidation of the ruthenium center in this material, and they have been studied intensively as anion redox model compounds. So there was a lot of existing literature on these materials that we could work from. So we went ahead and cycled these materials and put them in the NMR to actually see if the CEI that we grew during electrochemical cycling was actually able to give us any NMR signal at all. So it turns out that it gave us beautiful NMR signal. So we were actually able to do some very advanced NMR spectroscopy here using something called dynamic nuclear polarization, which allows surface sensitive NMR spectroscopy and do some very detailed 2D NMR structural assignments here. So you can see from this spectrum, we're able to see the PVDF in our composite, and then we're able to assign a variety of different electrolyte decomposition products in our CEI itself. So we have PEO, we have this peak here that comes from small lithium salts, so things like lithium acetate and lithium succinate. We have some different carboxy groups and carbonate decomposition products shown here as well. Also, we should mention that this spectrum was collected after only a single cycle where the CEI is still very, very thin. So by quenching the paramagnetism in this material, we were able to get very high resolution solid state NMR from this CEI. So because we were able to get such great signal from this material, we decided to study the CEI formation in this material as a function of cycle number, but also as a function of charge and discharge state. So if we just focus here on the charge state, what we notice is that we don't really have a change in our composition when we go from the first cycle to the 100th cycle. So we pretty much see the same amount of PEO that's deposited on the surface of our ruthenate after the first cycle. It pretty much stays the same until the 100th cycle. We think this is because whatever forms due to electrolyte decomposition happens due to oxygen evolution in the first cycle, which is known to be most prominent in the ruthenates during the first charge. And then not too much oxygen is evolved after the first cycle. The most striking thing that we notice in these experiments is that the CEI that's formed in charge versus discharge is very, very different. So in the charge state, we pretty much only have this PEO on the surface, but if we analyze what's actually deposited on the material in the discharge state, we see all different types of small lithium salts. We see a lot more PEO being deposited on the cathode surface. And so we became very interested in why this might be, although it's quite consistent from the first cycle to later cycles. So what we thought was, whatever is really forming in the first cycle is sort of dictating the interface chemistry, but it seems like whatever is forming is being passed back and forth during charge and discharge. This also matched what we measured during electrochemical impedance spectroscopy, where we could sort of monitor the interfacial resistance going up and down during charge and discharge in a very repeatable fashion that matched the compositional changes that we were seeing in NMR spectroscopy. So we were able to construct this molecular picture of anode cathode crosstalk and what's actually happening during charge and discharge is causing these changes in our interfacial resistance and also causing these changes in our interface chemistry during electrochemical cycling. Where during charge of the battery, what we actually think is happening is that some of the CEI is leaving. So lithium ions leave the cathode side of the battery, and they're actually taking part of that interface with them. So these very small lithium salts, these short chain PEO are leaving the cathode side. They're going over to our lithium metal electrode, and then they're depositing on the anode side of the battery during charge. Then during discharge, those same species come back to the cathode side of the battery where the CEI redeposits during discharge, the interfacial resistance goes up, and we see that we have this much more diverse CEI chemistry upon discharge. So this was all well and good, and we were able to get some interesting insights into how chemistry was actually dictating our interfacial resistance. But my student who was working on this project was also very interested in going back to the case of the NMC and really being able to apply some of this new knowledge to some more technologically relevant cathode materials. So she came to me and she said, we're making the batteries, we're doing all of the electrochemical cycling. And because we're doing that, we can really control the paramagnetism of the NMC811 as well. And we, in principle, can maybe do the same thing that was happening in the ruthenate case, but just control it with electrochemistry for the NMC811. So there was something unique to the structure about the ruthenates that was actually quenching the paramagnetism for one of the ruthenium sites that allowed us to get that high resolution solid state NMR. But in the case of the NMC811, we know that the nickel is going to participate in the redox during delithiation. And when the nickel participates in the redox, it should change from that 2+, 3+ oxidation state to the 4+ oxidation state. And the 4+ oxidation state is actually diamagnetic. So this should be very good for our characterization approach, where now if we analyze the battery at high states of charge, so if we go to high potentials, most of our nickel should be in the 4+ oxidation state. We know that we can keep our cobalt in the 3+ oxidation state. And then, of course, our manganese is still going to be in the 4+ oxidation state, which is paramagnetic, but our thought process here was that the manganese is making up only 10% of our paramagnetic centers. So our hope was that it was such a small part of our overall transition metal composition that hopefully this little bit of paramagnetism would be okay. So even with the rutheniates, it's still a little bit paramagnetic, and it was still okay to run our experiments. So we went ahead and we tested whether or not this hypothesis was actually true. First with EPR, where our EPR signal should be directly proportional to the number of unpaired electrons that we actually have in our system. So what you're looking at here is the EPR spectrum for the battery in the discharge state in red. So what you see here is this very broad signal here. This comes from the NMC811 particles. And then we have this sharp signal in the center. This comes from our conductive carbon additive. So there's also some delocalized electrons on the conductive carbon. And then we also have our black spectrum here. This comes from the composite in the charge state. So we charge these batteries to 4.6 volts. And then what we notice is that all of the signal from the NMC particles is completely quenched. So we don't actually have any EPR signal. We know that we still have manganese 4+ in there, but we don't actually have any exchange coupling with any more paramagnetic centers in the active particle. So basically the system is just so dilute that we don't actually get any signal anymore. Of course, we still have some signal from our conductive carbon. That's the sharp signal in the center. But all of the signal from the NMC811 has gone away after we charge the battery. So we went ahead and we cycle these batteries for 50 cycles, and then we go ahead and collect carbon NMR spectra. Whenever we do that, we see that we get well-resolved carbon NMR for a variety of different interface compounds that we would expect to be present in our CEI layers. So again, you can see that we see the presence of our PVDF from our composite. One interesting thing we note is that the ratios for our PVDF are a little bit off from what we would expect from the pristine material. We think that that's because some of this peak intensity here is actually coming from vinyl compounds that are present in the CEI itself. We see a peak here that comes from a mixture of our EC solvent and PEO. We see some carbonate breakdown products showing up here. And then we see lithium carbonate and some carboxy groups. One interesting thing that we see is that these carboxy groups and lithium carbonate, they also have these peaks out here that are highlighted in green and blue, and also denoted with these asterisks out here. These asterisks here represent that these are actually coming from a spinning sideband pattern. So these are not unique peaks. These are actually originating from the original carboxy group and the lithium carbonate here. So remember when I told you at the beginning, if the compound that we're interested in is very close to an unpaired electron, you'll get this spinning sideband pattern. That's exactly what we're seeing here. And because there is a distance dependent effect, we can actually calculate how close this is to a given compound in the composite. The one tricky thing is that based on this EPR spectrum, I just told you that we're getting 2 EPR signals. We can get one from our NMC particles, and we can get one from our conductive carbon. So now our NMC particles are also known to undergo this rock salt reconstruction at the surface of the particles, which will likely have some nickel 2+ in it. So there's likely some paramagnetic centers at the surface of our NMC particles. We also are getting a paramagnetic signal in our EPR from our conductive carbon. So from this initial spectrum, we can't necessarily tell whether this lithium carbonate and this carboxy group are bound to our conductive carbon or if they are bound to our NMC811. In order to figure that out, we ran a control experiment where we attached lithium carbonate to the conductive carbon that we used in the battery, and we attached it to Nmc811, and then we recorded the carbon NMR that we got from these samples. So what you see on the top here is the spectrum that we get out. So if we look at the spectrum corresponding to lithium carbonate attached to the conductive carbon, you can see that we actually don't see a spinning side band pattern. We actually also did not see a reduction in our T2 like we expected if it was impacting our NMR parameters in the same way. But whenever we look at our spectrum corresponding to the lithium carbonate attached to our Nmc811 particles in the bulk, we see that we get a spinning sideband pattern that looks almost identical to that coming from our CEI layer. So based on this information, we were able to conclude that the conductive carbon just isn't impacting our NMR parameters in the same way as our Nmc811. So we strongly believe that the sideband pattern that we see from our CEI is coming from the fact that our CEI is very close in proximity to the surface of our Nmc811 particles. And because we have this distance dependent effect from our sideband pattern, we can do a back of the envelope calculation to see where exactly we are in relation to our NMC particles. And from this sideband manifold, we calculate that we're about 1 nanometer away from the surface of our NMC particles. So about within this first nanometer, we can expect that we have carboxy groups and lithium carbonate at the surface of our Nmc811. So within this spectrum, we also have lots of different components that are not giving a sideband pattern. And we don't necessarily know if they are just in this outer CEI layer where they can do things like participate in crosstalk, or if they're actually bound to the conductive carbon additives, and maybe they have gotten there because they have reacted with those additives themselves. So in order to provide more insight into the lateral arrangement of our CEI layer, we do these XP measurements at Brookhaven National Lab. So what we're looking at here, again, is just spatially resolved X-ray absorption spectroscopy, where in this top image, what we're looking at is just a pristine electrode that hasn't undergone any electrochemical cycling. The magenta here is showing our nickel L edge. So this is coming from our Nmc811 particles. The cyan here is coming from our conductive carbon. This is what the composite looks like after 50 cycles. So analyzing at the same point that we collected our NMR at. And then we can pull out individual spectra from our conductive carbon and from our Nmc811 particles. Here I'm showing a map of our Nmc811 overlaid with the energy that corresponds to lithium fluoride. And here is the same map, the lithium fluoride overlaid with the conductive carbon. So what we can see from these maps is that we only really see lithium fluoride deposited on the surface of our Nmc811, and it's not really affiliated with the surface of our carbon additives. So we exclusively have lithium fluoride bound to Nmc811. It's not really detaching from the surface and going all over the composite. So one thing that we think might be happening is that the lithium carbonate can be reacting with hydrogen fluoride produced in the electrolyte, and this can be producing these localized lithium fluoride deposits that are on the surface of our Nmc811. Of course, in order for this reaction to happen, we have to have HF forming in the electrolyte. Our initial thought was perhaps our battery grade electrolyte might have a little bit of water in it. And it's very well known that PF6 can hydrolyze, form HF. And perhaps that's just reacting with our native lithium carbide or carbonate layer on the surface of our Nmc811. But whenever we took a look at our water content in our battery grade electrolyte, we couldn't get a reading that was registered on our Carl Fisher. We also took a look at our our electrolyte using fluorine NMR, we didn't see the presence of any HF in our pristine electrolyte. That's shown in the gray here. And it wasn't until we actually started cycling our battery, so this is Nc2 fluorine NMR, and it wasn't until we started cycling our battery at high potential that we actually saw the presence of HF in our battery electrolyte. So what we actually think is happening here is that whenever we start going to high potential, our cathode, our active particles, are evolving reactive oxygen species. These are very well known to be able to attack our electrolyte solvent. This electrolyte oxidation reaction can produce water. Then, of course, this water is what can participate in the hydrolysis of our PF6. And we think that this is actually where the HF is coming from in the system that's able to produce these localized lithium fluoride deposits on our NMC811 particles. And the presence of these lithium fluoride deposits on the NMC are important because, you know, lithium fluoride is essentially an ion insulator. So it has a very poor ionic conductivity. And the fact that it's appended to the surface of the NMC811 means that it's very likely contributing to these high impedances that we see upon extended cycling of the NMC811. And it's not necessarily just coming from this formation of the rock salt layer. It's also probably coming from the fact that we have lithium fluoride all over the surface of the NMC811 as well. And this is also probably why it's correlated with these high nickel stoichiometries, which are known to be more sensitive to moisture, and also correlated with these higher upper cutoff voltages where we're going to have more water formation. Okay, so we have a good idea of where the lithium fluoride and lithium carbonate are coming from on the surface of our NMC811, and it's very localized to these particles. But then we wanted to understand where the other carbon containing components were located that we see in carbon NMR. So this is the carbon X-beam spectra that we see after extended cycling. And this is from the carbon particles. This is from the NMC811 particles. And what you can see is that they essentially look identical. So whatever we have on the carbon particles is the same thing that we have on our NMC811 particles. So we started to think this is either telling us that the particles and the carbon are driving the exact same chemical reactions, or something else is actually happening in this system that's causing the entire composite to be covered with the exact same carbon composition here. So what we did in order to actually figure out what was happening at the surface of these composites in terms of the organic decomposition was an Nc2 Proton Nmr experiment. So here are the results from the Nc2 Proton Nmr. And what I'm showing here is that as soon as we start cycling to high potentials, we see the formation of a wide range of vinyl decomposition products. We also see the formation of this DMD-OHD, which is just a carbonate breakdown product. So these vinyl products are likely contributing to this resonance here at about 120 ppm. But the fact that we see them in situ proton NMR, which is primarily monitoring the soluble decomposition products, indicates that even though these vinyl products might be formed due to electrolyte oxidation at the NMC811 surface, they are soluble enough that they can detach from the particle surface and then be floating around in the electrolyte where we can actually detect them in this experiment. And because they're floating around in the electrolyte, they don't really care where they deposit onto. So they're depositing sort of indiscriminately onto the outer CEI of the NMC811 particles. So they're depositing on top of that lithium carbonate and the lithium fluoride. They're also depositing on the surface of our carbon additives. So on top of our conductive carbon and on top of our PVDF, sort of giving this false notion that the carbon additives might be playing a role in producing these molecules, but they're actually just these soluble components and they don't really care what they stick to at the end of the day. So what we're interested in looking at now is, the fact that things like lithium carbonate, lithium fluoride, but also these vinyl compounds are attached to the surface of our NMC811. These can all impact the lithium transport in and out of the particle itself. But then we also have these vinyl compounds that we know are also building up as this sort of gunk all over our carbon additives as well. And at the very beginning of the talk, I told you that we're adding these carbon additives for a reason. So we have our polymeric binder to hold our active particles together, and we have our conductive carbon so that we can improve the electronic conductivity of our composite. So what we're interested in investigating now is, if we have the buildup of these organic decomposition products or other electrolyte decomposition products on the surface of our composite, how is this going to impact things like electronic conductivity or binder swelling that may also be impacting our battery performance in ways we maybe didn't think about before? So just some food for thought. But I'll finish there. I would just like to wrap up by thanking my PhD student, Julia, who did most of this work, and then the funding sources. Also, I would like to thank Jurek Sadowski, the beamline scientist at Brookhaven, who helped us collect all of these XPeam images. And I am happy to take any questions.
Yeah, wonderful talk, Lauren. Thank you very much. It's absolute chemical heterogeneity, chemical maps, and information is all around. Thank you so much. It's just amazing. So I'll probably let Debanjali handle any questions you might have in the chat or anyone. So do you see any questions, Debanjali?
Not yet.
Okay, no problem. So I will start with one, Lauren, to break the ice perhaps a little bit. So I have a couple of questions, but one thing is a little bit in this particular technique, what are the opportunities and challenges you see for solid-solid interfaces? Especially, let's say that you have a solid electrolyte-based cathode, maybe the same NMC, but now it's a solid electrolyte, and then you pair it with a solid electrolyte. So there are pretty interesting interfaces, and there are interfaces. Could you comment on your thoughts and perhaps any thoughts you have? So
that's a great question. I think there's a lot of opportunities, and I actually think a lot of things become easier because the solid reactions that you have become a lot slower in many senses. If you're looking at chemical reactivity, but even electrochemical reactivity, the timescales are just like a little bit slower than some of the kinetics that you have in at the liquid solid interface. So I think that there's some opportunities to do some really cool, interesting studies there that I think are exciting and would love to get involved in. And then also in terms of NMR, but then also in terms of like some of these XPeam measurements and ultra high vacuum, I think there's also a lot of opportunities to study solid-solid interfaces, because the challenge with looking at the liquid interfaces is always that you have to be in ultra high vacuum. But if you're looking at a solid-solid interface, it's much easier because you don't have to worry about sucking away your solvent. So.
Oh, so wonderful. So that's good to hear. So essentially, the perhaps these techniques would be very useful, and not only that, it probably can tell much more. Probably.
I think it has the potential to.
Wonderful.
Sure. Yeah.
And also, one more question maybe I could ask here. It's your take on chemical crosstalk. It's wonderful. It not only forms a great hypothesis, but also exactly the mechanisms that you just showed. And particularly so for such high voltage sort of a cathode materials and sort of oxygen evolution and all of those things. Now, if we now sort of extrapolate this to a little bit of a scenario where things are the same chemical the heterogeneities that are out there due to the formation of the passivating layer, whatever CI. Now, when it comes to thermal instability, such as exposed to a high temperature, then those things could lead to that abuse scenario, thermal instability. So my question here would be, that could this technique, sort of NMR technique, could be paired with perhaps saying or giving us some insights how this chemical heterogeneity might impact your thermal instability if exposed, perhaps, to an anomalous condition, which could be high temperature, or the role of lithium plating. When I see this interface, I get to ask this question. I try to ask this question because you add plating, the lithium plating is, of course, that will be more on the anode side, I get it. But then you have the ACI and plating. Could, from your technique, what are the things that we can kind of infer or some insights that we may be able to get? Just again, these are a few generic questions, but I thought very, very interesting when I look into it at the time.
I think because, you have the molecular structures now, so you could, look at the empirical thermal stabilities. But what I would do is just run the high temperature experiment, and maybe it's bad to do because maybe it creates a mess in your spectrometer, but or inside your magnet. But
is it even possible to do that? Let's assume that it is possible. Is it even possible to do that? A little bit of high temperature exposure, really, so that you can really map a thermal instability on top of that as well?
Yeah, so it depends on your equipment, but like so most of our probes can go to about 125 degrees C. Right now we're running some variable temperature experiments just at 60 C, which is typically where you want to test for like EV applications.
Mm-hmm.
But yeah, I would say you can definitely study that at higher temperatures as well.
That's wonderful. So somehow being able to map that or extrapolate that will be something very cool, of course. No, this is wonderful. And let's add lithium plating to your ACI.
Yes.
What could it tell us a little bit more? What's your thoughts?
Yes, we have some work on that. And we're currently running some of these experiments too. So the high temperature stuff that I mentioned we're running is like NMC versus copper and plating lithium metal, and specifically trying to study the lithium plating behavior in these systems. Yeah.
All right. So I look forward to those papers, perhaps. No, this is good. So very good. This is absolutely wonderful. Thank you. I'll stop here. Any other questions from the audience? You could certainly share now.
Yeah, we have one question on the crosstalk from James. What do you think drives the reversible deposition of those oligomers? Are they solvating lithium cations?
I think it's solubility, because, or at least that's our working hypothesis, because it's usually the small stuff. It's also probably related to their charge and coordination to lithium as well. Or at least that's my intuition. It's a lot of the salts that we're able to coordinate. So they're small, and then they're coordinating to lithium as well.
Okay, thank you so much. Yeah, so we just had one question in the chat box. Oh, yeah, there's one more. Metal fluorides, not just lithium fluoride, but also nickel and manganese based, are often reported as nickel rich NMC CEI decomposition products in with long-term cycling. How easy or difficult would it be to measure these quantitatively with 19F NMR? What could be other alternatives here?
That's a really great question. We're currently preparing a paper on this. It turns out these things are really hard to measure with fluorine NMR because they're so paramagnetic. And it's not that they can't be measured, it's just that whenever they're in the surface, they're typically at such low quantities, and then you have these very broad line shapes. So signal is low, line is broad, so you don't get very much signal intensity. So the way we're going about characterizing that is, this is mostly through XPEM and trying to understand where it's located in the composite. And then we can assign the type of fluoride that it is based on both the fluorine edge and the metal edge as well.
Thank you so much. So that's all for the questions in the chat box for now.
Lauren, may I ask one quick generic question?
Yeah.
So for example, for lithium metal as compared to sodium metal or any other, maybe potassium or whatnot, what are the kind of challenges you typically see in your work or perhaps envision with this technique? Because you will have, again, similar story about ACI and this, the whole kind of a chemical map would be all over the place. Could you comment on that?
Yeah. So the thing that we studied the most in my group is potassium batteries and lithium batteries. So that's what I feel most prepared to comment on. And I think the lessons we have learned there is that potassium SEI is just so, or maybe I should say the electrolyte formulation that you need to generate a good SEI in potassium is just so different than what we need in lithium. So for example, we found that when we add FeC to our potassium batteries, they immediately die, which was very unexpected to us. But it turns out we're forming KF and potassium carbonate, which are just not very good potassium ion conductors. So it's not going to form a very stable SEI that's going to allow reversible intercalation or plating. So that's a challenge. What we're seeing now, and we just started collecting some of this data, is that, some of these additives that have been reported for lithium, and, some of these additives that have been looked at as flame retardants for lithium, that ended up performing very poorly in lithium, are now looking quite good in potassium. So it's just like the opposite of everything, I guess, has been the story that we have sort of learned there. And I think what I've gained from the literature in terms of sodium is that a lot of the salts are just so soluble that you deposit on the surface. So it's not stable at all. And how do you strip and plate in a way that is reversible when you can't form a stable SEI? It's really hard. So.
Well, that's wonderful. We are seeing some very strange things when we just switch from lithium to sodium, and even the whole electrolyte is different ballgame than, or probably that means the interface I'm talking about. So yeah, that's amazing to hear. So I think that could be one opportunity to even sort of think about some experiential collaboration in that space, because that will be very interesting and so much unknown and so much. Actually, that's the FeC. The story of FeC suddenly works differently for sodium from some of the experiments that one of my students, Sushmita, right? She's probably here online, yeah, as he's doing. So it's kind of very interesting. So I think that kind of corroborates with your comment and learning that you have from potassium. It's kind of very different.
We just published a paper on that not too long ago. So
wonderful. No, I think I noticed about your potassium that you were working on that. Sushmita, go ahead. Sorry.
Yeah, Mr. Professor Marbella, I saw your paper about KF, and so we were also trying to explain, like when we added the FeC, why the cell died. It's like completely opposite trend from lithium, and I found your paper where you explained the KF is the responsible one, and I'm like, yes, so NAF is the responsible for the sodium as well. I wanted to ask you, like, did you change the ratio or the concentration of your FeC, and you saw for all the cases, or is it like one particular case you saw this cell?
That's a good question. I think my student might have played around with a few different concentrations of FeC. I will have to double check with him though.
Okay. Yeah. So I was wondering if, because I only used like very high, like 10 to 30% of concentration. So I was wondering if that's one of the reasons. Probably I saw like a lot of NAF and the cell was dead. So what was the percentage you used, volume percentage? Do you know?
Oh, off the top of my head, I don't remember what 5%?
Is it? Okay.
It's in the paper. But I think it was, I forget what we landed on, but I think it was 5%. I know what's most fresh in my mind is the additive we've been looking at recently, and I know we've played around with lots of different percentages, and we see that the trend holds for small amounts, for large amounts. It's just, you get slight differences, but it's pretty interesting in that sense. Yeah.
Thank you.
All right. So Devanjali, any other questions from the chat box that you might find? Or
No, that's all
all
from the
right.
chat
So
box.
in that case, Professor Marbella, it's wonderful once again. Just as always, wonderful presentation. Learned a lot all the time.
Thank
And thank you very much for finding time to speak with us today. Over to Devanjali. Any concluding remarks or comments?
Yeah, thank you so much for your wonderful talk, and we really enjoyed having you with us today. And we hope to welcome you in person next time
Yes, that
at
would be
Purdue.
great. Thank you
Thank
so
you.
much.
Yeah, thank you
Bye.
so much. Bye, everyone.
Bye-bye.